All right, so this chapter will talk about waves. Um, Last chapter we talked about oscillators, simple harmonic oscillators, and waves. You can think of them as a whole bunch of oscillators in choreographed. Okay. So let me show you a simulation of what we are interested in studying. Yeah. So here's a wave that's traveling on a string. Okay. So let's see what is happening. For a wave, a disturbance to travel in a medium, okay, what you have to have is an external source disturbing the medium. So what is this guy doing? So for instance, if I pound the table, I'm putting energy into the system. Okay. So this oscillator is putting energy into the system, and this energy is being carried away. Okay. So when a wave travels in a medium, it's carrying energy. Okay. Now, what is this green dots telling you? What are the green beads telling you?
Your period.
I'm sorry?
Your period.
Well, they're oscillating, but that green bead is not going anywhere. Okay, so what it's telling you is when a wave travels through a medium, it's the disturbance that travels. The medium itself is not transported. Okay? So it's like a wave in a stadium. When people go up and down, people don't travel with the wave. Okay, it's the disturbance that travels. Okay, so a wave carries energy. Now, in this medium, which way is the wave traveling?
To the right.
To the right. Okay. Which way is the Which way are the particles of the medium oscillating?
Up and down.
Up and down. Okay. So this is what is called a transverse wave. In this transverse wave, the medium particles of the medium are oscillating in a direction perpendicular to the direction of the wave travel. Okay. Now, in solids, this is possible. In liquids, you can only have waves. In fluids, that is liquids and gases, you can only have waves where the particle oscillates parallel to the direction of wave travel. Okay? So this wave is called a transverse wave. This wave is called a longitudinal wave. Okay? In a wave where the the particles of the medium oscillate parallel to the direction of wave travel, those are called longitudinal waves. Okay? All right. So what I'll do is, okay, so now I'll do something. I'll reduce the tension in the string. Okay? So see what happens. Okay, now you see the wave is traveling to the right. Maybe you might not be. Can you tell, maybe it's hard to tell, what happened to the speed of the wave?
The rate of energy transfer slowed down.
Very good, very good, okay? So, the more tension there is in the string, the faster the wave will travel. You'll learn this, okay? All right. All right, so when a wave travels in a medium, it's a disturbance that travels, and all waves carry energy, okay? And you've experienced this. You go stand outside in the sunshine, you feel the warmth. That's the energy being carried by the electromagnetic waves when you absorb it. Okay? All right, so we will study these properties. All right. So there are mechanical waves. Mechanical waves are waves that need a medium to travel in. Okay. So the wave that you saw on the string was a mechanical wave. Okay, and the sound wave that's coming to you is traveling through this medium. It's a mechanical wave. Okay. There are electromagnetic waves that will travel through vacuum. They don't need a medium to travel through. Okay, and they're called electromagnetic waves because they contain both electric and magnetic fields. Okay. And and we'll talk about them in physics too. Okay. And then there are matter waves. These are waves associated with matter particles, and you talk about them in quantum mechanics. Okay, so for instance, if you know, classically we are conditioned to think like so. If you shoot a beam of electrons, the electrons will have a wave nature associated to them, and the wavelength of this wave will be equal to h, Planck's constant, times the momentum of the particle. Okay? H divided by mass times velocity. So, all right, so now, okay, so here's a tangential, here's a related fact. So, how do I see this object?
As a solid,
You know, how was the physical process of seeing happening?
electromagnetic radiation from light lands on it, some of it reflects back in
Right.
color,
Okay.
hits your eyes.
Right, so light, right, our friend says, light falls on it, this reflects, and then you see it, okay? So you need a probe, a wave to see it, okay? Now the question is, what is the smallest object I can see with light?
Size of a photon,
Okay, the smallest object you can see is the size of the wavelength, okay? So if an object was smaller than the wavelength, you couldn't see it using that probe. So what if you wanted to see a smaller object? I'm sorry? No, you use a probe that has a smaller wavelength. That's what you gotta do. So with light, the wavelength of light is about 6,000 atoms big. Okay? So if you wanted to see something like 100 atoms, you can't use this visible light. But you've seen pictures of atoms. Okay? So what do? They use X-rays. X-rays have small wavelengths, so if you want to see stuff the size of an atom, you use X-rays. What if you want to see stuff smaller than that? Well, I guess small stuff. So you can use electron beams. So the wavelength associated with them is h times m, h divided by m over e. So the faster the electron beam goes, the smaller the wavelength and the smaller the stuff you can see with it. And that, you've heard of electron microscope? That's the idea. That's where okay? All right. Okay, so when a wave travels through a medium, matter is not transported. Okay? Only the disturbance travels. Okay? All waves carry energy. Okay, here's a water wave. So we live by the ocean, and you've all seen water waves. And water waves, it's the particles on the surface are actually going in a circle. But last chapter you studied that uniform circular motion is really two simple harmonic motions. It's this motion plus this motion. That's a transverse wave, and that's a longitudinal wave. Okay? So this water wave is a combination of both transverse and longitudinal waves. Okay? So what are transverse waves? Waves where the wave is traveling to the right and particles are oscillating perpendicular to the direction of travel. Okay? Those are transverse waves. Longitudinal waves are waves where the particles are oscillating parallel to the direction of travel. Okay? And in fluids, what are fluids?
Liquids and gases.
Very good, my friend. In fluids, fluids cannot sustain transverse waves. They can only sustain longitudinal waves. Okay? So fluids cannot bear shearing stresses. Okay? So in fluids, you have only longitudinal waves, and in solids, you have both transverse and longitudinal waves. All right, let me show you a simulation of longitudinal waves. Okay. Did you have a question? Okay, just thinking. All right. Thinking is allowed. All right, what were we doing? We were going to do Dr. Russell's page is pretty good about for acoustic oscillations. So here's a wave traveling in a fluid, in a gas. Okay, so to make a sound wave, what you do is all you need is a diaphragm, and so make the diaphragm vibrate. So here's a diaphragm vibrating, and you see what it's doing is it's creating high pressure and low pressure regions. Okay, and so this pressure wave is traveling to the right. And now if you could see an atom, again this is just a simulation, so there's that red dot, and you can see that that atom oscillates back and forth like that, parallel to the direction of wave travel. Okay, and this is a longitudinal wave. So if sound wave traveled through water, this is how it would, the water molecules would oscillate parallel to the direction of travel. Okay. And here's a transverse wave travel, but this, you can't have transverse wave through a fluid. This is a fluid. Okay. Well, all right, so this is, I guess, meant to be a solid. Okay. So water waves, in a water wave, you can see that each molecule is going in a circle. Okay. And as you go deeper in a water wave, the motion becomes elliptical. Okay. This is these are Rayleigh surface waves. This is actually showing earthquake waves, surface waves on Earth. So this is not in a liquid. On a liquid in the ocean, they're going in circles. Okay. All right, so we know what are transverse waves and we know what are longitudinal waves. Okay. So water waves on the surface, water molecules go in circles. Okay. Now we'll define these two terms, amplitude and wavelength. Okay. So the wavelength is crest to crest distance. And amplitude is the maximum displacement from the equilibrium position. Okay. So amplitude is related to energy. So when you talk louder, more energy is being transmitted, and I increase the amplitude of the wave. Okay. The wavelength, for instance, in light is related to the color of the light. Red light has longer wavelength than blue light. Okay. And shorter the wavelength, more energy the light has. Okay. All right. Period, denoted by T, is the time it takes for a particle to complete one oscillation. It also, if you're standing here, it also is the time for one wavelength to pass you. Okay, so the period can be defined in two ways. It's the time for one complete oscillation, or it's the time for one wavelength to pass you by. Okay. Frequency, denoted by F, is inverse of the period. What do you think the frequency is?
A period per second.
Oscillations per second. Okay. So how many times it'll oscillate per second? Or also, if you stand here, how many waves will pass you per second? If the frequency is 10 hertz, then 10 wavelengths will pass you in 1 second. Okay, so now you know what transverse waves are, longitudinal waves, you know the period, wavelength, and frequency. Okay? We'll define two more wave parameters. They'll be useful for later mathematical description. This is called a wave number, the first one. The wave number is denoted by K. and it's 2 pi divided by lambda. All right, and the other parameter we'll define is angular frequency denoted by omega. It's 2 pi times f. F is the frequency of the wave. Okay? So angular frequency is 2 pi times the frequency of the wave. All right, so now what we want to build is we want to do the following. So we want to mathematically describe this traveling wave. Okay, so let's prepare for that. All right, so here's a pulse. All right, here's a function. Okay. All right, let's do this. All right, here's a function. All right, I want to shift this function to the right by amount d, by distance d. How do I do that?
Plus D inside the.
I'm sorry?
You just add D into the.
It's subtract d. Okay. Okay, so fx minus d shifts this function a distance. Okay. And that distance is d. If you want to shift it to the left, what do? X plus d. Okay. So now let's do the following. You know how to shift it. Well, I want to be a little more ambitious. Instead of shifting it, I want it to travel at velocity v. How would I do that? I'm sorry? No. Okay, so if you want it to travel in velocity v, after 1 second, how far will it be? What is the distance it will have traveled? Distance is v times t. After 1 second, it will be v times t. After 2 seconds, it will be 2v away. Okay? So here's a simple way to make it travel to the right at velocity v. There you go. Now you made the pulse travel to the right.
Okay, I found this on the web for what is the distance. After 1 second, after 2 seconds, it'll be a simple way to make a right.
Thank you, Siri. So how do you make it travel to the left then? Yeah, so f. Yeah. All right. Okay. Can anybody give me this function? Write this.
It's a sine wave.
Okay, so fx is sine. So 2 pi lambda x. Okay, so that's why we define this k parameter k. We'll call that k, but I'll write that in a second. Let's make sure that this is true. So for x equal to 0, this is 0. Sine of 0 is 0. For x equal to lambda, this is 1. Sine of 2 pi is 0. Okay? For x equal to lambda by 2, x equal to lambda by 2, this will become pi. Sine of pi is 0. Okay? So here's this function does describe this wave. So this is a, and remember that's why we defined k, kx. So there's our function.
Is
There.
it ax times sine k or is it sine of kx?
Sine of kx.
Okay.
Okay. So A is the amplitude of the wave. Okay? So but you already learned how to make a function travel to the right. So can I make this travel to the right at velocity v? Okay, so what would that be?
A of sine of k times x minus vt.
Very good. Very good, my friend. Okay? So xt is a sine kx minus. What did your friend just do? He just did this. He described that. All right? So you learned to do that. Yep. So now if we set up a wave on a string, you know how to mathematically describe it. Okay? And of course, if you wanted it to travel to the left, what do? Yeah, plus VT. There you go. Okay? So it wasn't that difficult, was it? All right? All right. So so you want a function traveling to the right at velocity v, that's x minus vt, so now let's see what this is. Okay, let's go back to there. So here was our function. Okay, so in a second you'll see that the velocity is related to frequency and wavelength like this. It's the velocity of a wave is frequency times wavelength. Okay, and omega, remember the other parameter we defined was 2 pi times f, and k, the wave number, was 2 pi by lambda. Okay, so I'm going to write this in terms of omega and lambda. So frequency is omega divided by 2 pi, angular frequency, and lambda is 2 pi over k. Okay. So the velocity of a wave can be written as frequency times lambda or omega divided by k. Okay, let's substitute that in there. Okay, what is this guy, by the way? I forget.
A description of how the pulse is traveling.
It's a sine wave traveling to the right at velocity v. Okay, that's what that is. Okay, of amplitude a. And so let's see, xt equal to a sine kx, except that v is omega by k t. Okay. So this will be this k, it'll be kx, and the k will cancel with that. Okay. So it's sine kx minus omega t. Okay, what was this guy? It was a sine wave traveling to the right at velocity v, and this is equal to that. So this is a sine wave traveling to the right with velocity v. Okay, and that's what we wrote there. Okay, so this is the convenient way of writing it: a sine wave traveling to the right with a velocity equal to omega by k. And what would be a sine wave traveling to the left? Plus omega t. Very good. Okay. All right, so this is a sine wave traveling to the left with velocity v. Okay. All right, this slide shows you the velocity is f times lambda or omega divided by k. Okay, so what you're looking for is, this is called the phase of the wave. Okay, and what you want is, see, as t increases, x increases. Okay, so what you want is this phase to be constant. That'll give you the phase velocity. Okay, so as t increases, where is x located such that this remains constant? Okay, so there we go. We'll set this constant and take the time derivative of that. So k and omega are constants. Dx by dt minus omega equal to 0. And so dx by dt, which is the velocity of the wave, is omega divided by k, which is equal to f times lambda. Okay. So that's the velocity of the wave. Okay. And here's a sine wave traveling to the left. Mhm. So it's this wave traveling to the left at velocity v. All right, so we've learned a whole bunch of things about a wave. Okay, we've learned how to mathematically describe it. We know what its velocity is. We know what its frequency, period, amplitude, and all that are. Okay? Now we'll relate the speed of the wave to the parameters of the string. So we're still talking about velocity of the wave in a string. Okay? It turns out that the velocity is related to the tension in the string. And what do you think that is? All right, what do you think will affect the velocity of the string? Okay, so let me give you a hint. Go ahead.
The mass of the string.
Very good.
It has
Very good.
inertia.
Very good. Very good. That's what I want. Okay. So heavier the string, slower the speed of the wave will be. Okay. So this is mass per unit length. Okay. So greater the tension, faster the wave will travel, and mu is the mass per unit length of the string. Okay. Heavier the string, slower the wave will travel. All right, so a wave is a whole bunch of harmonic oscillators. Okay? And a harmonic oscillator, when a mass is attached to a spring, when it oscillates, what does it have? It has kinetic energy and potential energy. Okay? So I'll draw this horizontally. Yeah. So it's oscillating like that. When is the kinetic energy the maximum?
At equilibrium.
At equilibrium. And when is the potential energy the maximum?
At peaks.
At the peaks. Okay. All right. So here's a string. There was the string. Think of it as a rubber band. Okay. When does it have potential energy? When you stretch it. Okay. So here was the undisturbed length of the string, and then the wave is traveling on it, and we are looking at a snapshot. So here's a snapshot of the wave, and look at this. This string is stretched. It was that length, and now it's stretched to that length. So it has maximum potential energy, and it's at rest now. Okay, so, and then as it's vibrating, this thing will go through like that, this thing will go through like that. When it's back to its original length, what is the potential energy of that string?
Minimum.
0, and it's going at its fastest. Okay? So that's what's happening. So you can think of this one wavelength as doing a unit. You can think of it as a unit and doing simple harmonic motion. Okay? Now that's when the energy is parallel, but you can think of each element is also doing a harmonic motion. It's also vibrating in a harmonic fashion. Okay? But the potential energy and kinetic energy are parallel when you think of it as a wavelength. Okay? All right, what does a wave carry? Energy. Okay? All right, so what we want to ask is the following question. We are going to stand here, and how much energy passes you per second? That is the power. Okay, energy per second is the power. All right, so the average power, so when a wave is carrying energy, if you stand there, the average power, that is the energy passing you per second, is 1/2. Mu is the mass per unit length. V is the velocity of the wave. Omega is the frequency, angular frequency, and A is the amplitude. Okay, so that's the average power. Okay, these are properties that depend on the string, and these are properties that depend on the oscillator, the thing that is pumping energy into the medium. Okay, so this is property of the medium, and this is property of the external agent. Okay, so see the amplitude is controlled by the external guy. Okay, so when this guy pumps harder, you're increasing the amplitude, and the frequency is also controlled by him, but the velocity and mass per unit length are dependent on the system. Yeah? All right. The dependence of average power on the square of the amplitude and frequency. See, this is square of the amplitude and square of the frequency. That's a general result, and it's true for all types of waves. Yeah. All right, so if you go back and look at your notes from the previous chapter, here's this system, and if there's no friction in the system and you pull this guy up to the side, what is he going to do? He's going to oscillate. You guys remember we mathematically modeled the behavior of this system, and that mathematical model was a very good, my friend. It was a differential equation. And what we said was this position, the configuration of the system, was determined by this differential equation. Yep. And then you learn to solve this differential equation, and here was a solution. Okay, so you could solve the position of this as a function of time, and now you knew everything about the motion there was to know. Okay? So again, what was the deal? So what we were learning to do was, you had a system, you came up with a mathematical model, you came up with a differential equation that described the behavior of that system. And why did you do this? Why did you do that? Just because you were bored? Well, if you want to study this system, you can set this up in lab and try and measure its position as a function of time. That would be hard to do. But you were smart. You set up this equation, solved it, and now you know the behavior of the system. You didn't have to get your hands dirty. Okay, so that's why you set up mathematical models. Did you guys understand that? All right. We want to do the same thing with this guy. we want to come up with a mathematical model describing the behavior of the system. All right. So this is a little more complicated. So let's say we take a snapshot of this. Okay, so let's see. Oh, there you go. Okay. So to describe this, see, there is the y position of the string as a function of x, right? So here is y as a function of x. And now if I start that, see that y position depends on x as well as time. Okay? So the y coordinate of that thing depends on x and time. Okay. So here's the string, and this y coordinate is a function of x and t. Okay. And we want to, just like in this case, the x position was a function of only time, and we wanted to find the differential equation satisfying that position, the configuration of the system that satisfies the differential equation. We want to do the same thing for this. Okay. Now we're not going to derive this. I'm just going to give you the answer. All right. So it turns out that del square y okay, what does del y by del x mean? What does this mean?
Differential of y with respect to x.
It's a partial derivative of y, okay? Yeah. So when you have a function of multiple variables, okay? So let's make sure we understand this. Okay, so for instance, we'll give it xy equal to x squared y cubed. I'm just making up a function, okay? And what does del f by del x mean? What is del f by del x?
It's the x partial.
I'm sorry?
The x partial.
Right, okay, so what is it?
Just 2xy cubed.
2xy cubed, very good. So what we are doing is treating the other variable as constant and just taking it with respect to that. And what is this guy? Okay, so if you evaluate it at this point, how is f changing as you go parallel to the x-axis? Okay, that's what that means. Okay, and what does del f by del y mean? What is del f by del y?
Taking the derivative of f.
Okay, what is it?
to y,
Yeah, and what is it?
X squared 3y squared.
Very good. Okay, and what that is telling you is how is f changing as you go parallel to the y-axis. Okay. So similarly, so del f del y by del x means how is y changing with respect to x? You're holding t constant and so on. Okay, so this is equal to 1 over v squared del square y and this is the wave equation. Okay, so that vibrating string, any vibration in the string, okay, any solution satisfies this wave equation. Okay, where v is the velocity of the wave on the string. And remember, the velocity of the wave was related to the tension in the string and the mass per unit length of the string. All right, so that's what, so here's the wave equation. Okay, so that's the mathematical equation that describes the behavior of this vibration in the string. Okay, and solutions are of that form. So you have waves traveling to the right x minus vt, or waves traveling to the left x plus vt. Okay, you can have any form of wave and you can make it travel to the right or to the left. Okay, this is a partial differential equation. Okay, this is a linear partial differential equation. Okay? So there's no square term like this. What this means is if it's a linear partial differential equation, what that means is if you have two waves traveling, you can add them and the sum of them also is traveling, is also a solution. Okay? So you see, so the fact that this is a linear differential equation means the following. Okay, so this wave is traveling to the right on there, this wave is traveling to the left, and when they're on top of each other, they're add. And look at this, when they're passed, see this wave is exactly like that. This wave is exactly like that. They didn't alter each other. Okay? All right, so that's a consequence. Okay, so, and also when they're right on top of each other, you're just adding them. Okay, so if what that means is y1x plus t is a solution to that wave equation, y2x plus xt is a solution, then y1 plus y2 is also a solution to that wave equation. Okay. Interference. So that phenomenon is interference. When you have two waves at the same location, you just add them up. What if you have three waves at the same location?
They all.
Add them up.
Add them up. You know how to add two numbers, you know how to add three numbers, you know how to add 100 numbers. So you can have 100 numbers, we can all talk at the same time, and we can figure out what Raza hears. It's no big deal, okay? You just add up all the signals, all the waves. All right, let's, I can show you. So you see, they added up. And once they go past each other, they have not changed each other's nature. Okay? All right. So constructive interference occurs when the resultant wave, when two or more waves combine, the resultant wave, when two waves combine, the resultant wave is bigger than either of the waves. Okay, so this is a constructive interference. This is, you have destructive interference when two waves combine, so you have to have two opposite sine waves. When two opposite sine waves combine, the resultant is smaller than the bigger wave. Okay? So this is destructive interference. And of course, if you have waves of equal amplitude combining, when they combine, when they interfere, the wave will cancel and you'll have zero sound. So for instance, this will happen. So let's say you have a speaker here, and this speaker sends out a wave like that. At this point, it's reaching with a crest, and this speaker, this wave reaches with a trough. What do you think will happen here? I'm sorry? They'll cancel each other, okay? And this seat will get no sound. And if you sell that seat for $500, that person will be very upset. Okay? All right, so for instance, you can have two, so if these two speakers are out of phase by 180 degrees, what that means is when this guy sends a crest, this guy will send a trough. So that's 180 degrees out of phase, okay? So when that happens, along the center aisle, every frequency will cancel. Okay? So in a studio, then you don't put, in a theater, you don't put any seats on the center aisle. Okay? All right, so that's constructive and destructive interference. So now we'll learn how to add waves. So here's, what is this guy? This is And this is a wave with amplitude A. There is the wave number. There is the angular frequency. Which way is this wave traveling?
Right.
To the right. How about this wave? This wave is also traveling to the right. This is just a phase shift, okay? So when this guy at t equal to 0, x equal to 0, if he started off like this guy will start off, so if the first wave started off like that, the second wave, because of this phase shift, maybe is starting off like that, okay? If this phase shift is 0, if this is 0, then he would also start off like that, okay? So if the phase shift is 0, they're both starting off identically, okay? And you add them, you get a resultant wave like that. If the phase shift, if the phase shift is pi, what pi means is when this guy is traveling, one is traveling like that, the other guy is traveling like this, okay? And they're both traveling to the right, and they cancel each other. Okay? So if you play two speakers with a phase shift of 180 degrees, the waves are canceling in that direction. Okay? And you won't hear any sound. Okay, so that's what this is showing. And there, this is for a phase shift to 2/3 pi. This is the resultant wave. Okay, so here's this wave added to this wave, and the sum of the two waves is this. And you see there is the amplitude depending on the phase shift. And here is the wave, traveling wave part, and it's still traveling to the right. Okay. Okay. So when the phase shift is pi, they interfere destructively. So when one wave starts off like with a crest and the other wave starts off with a trough, as they travel, they're canceling each other everywhere. Okay. All right. So you see, when you added two waves traveling in the same direction, you would have to use trigonometric identities to come up with this. And let's say if you had to do add more than two waves, then it can get to be a problem. Okay? So we want to come up with the easier technique to add waves. Yeah. Because, we can have a situation where we are all talking, okay? And we want to be able to add all those waves. Okay. So trigonometric identities are good, but they can be a pain in the neck. Okay, so here's an easier way to do it. By the way, let me remind you of here's a vector A. What is the y component of this vector?
A sine theta.
Mm-hmm. AY is A sine theta. All right, you see, so there the displacement of that wave is, you can think of this as the amplitude of the wave, sine of this angle. So it's like the y component of this vector. Okay, so if you want to add two waves, A and that, and their phase difference is phi, okay, so there's wave 1, there's the phase difference phi, and there's wave 2, okay. You add the two, and there's the net resultant wave. And as t increases, see this angle is decreasing, so you make the wave rotate like that. And this wave plus this wave is that resultant wave. And the instantaneous value is, as this thing rotates, it's the y component of that. And that's what that is. So ym sine k minus omega t plus beta is the phase difference. Okay. So that's how you easily add multiple waves rather than having to use trigonometric identities. Okay, so these diagrams are called phasor diagrams. Yeah. Again, that's So you will, so that's a useful technique to know. All right, what is this?
Oil spill?
I'm sorry? Yeah, it's oil. After it's rained, it's oil slick on the road. What are those colors? Hmm?
It's a rainbow, it's a light refracting different ways in the pattern, not sure why.
All right, so we want to understand that. Okay? All right, so this thing is, and I'm looking at glasses. Again, everybody's rich and has non-reflective coating. All right, so on glasses, they put a thin layer of plastic so it is non-reflective. And I'll tell you in a second what that is, so you can see everybody's eyes clearly. Okay, you paid extra money for it. I don't know if you realize that. Yeah. All right, so what is this guy? Let's understand what is happening here. Okay, so so here is this oil sitting on water. Okay, you send a beam of light. When a beam of light hits a medium where the velocity changes, okay, and this will only happen when velocity changes. Okay, so when it hits a medium, part of it is reflected, and part of the energy goes in here, and then again it's hitting a interface where oil-water interface, part of get reflected, and then this will come out like that.
The velocity will only change when it passes through another medium, right?
So, yeah, so for instance, when light goes into water, its velocity changes. When light goes into glass, its velocity changes. And so part of it is reflected, part of it is refracted. Yep. And in the second medium, its light was going this way. If it's going slower, it'll bend towards the normal. That's called refraction. Yep.
What do you mean light slows down? I thought it always moved at constant speed.
It's in vacuum. In a given medium, it goes at the same speed. So in vacuum, the speed of light is 3 times 10 to the 8 meters per second, roughly about 200,000 miles an hour or second. In water, N is 1.33 for water, or we'll do glass. For glass, refractive index is 1.5, so V is C over 1.5, which is 2 times 10 to the 8 meters per second. So it slows down by 33%. Okay. All right. So we're trying to figure out that the colors, yep.
So if like you shine a beam of light through like oil and water, one will come first, like noticeably?
I'm sorry?
Or like with sensors? Like through two different mediums?
Yeah, well, okay. So this beam came to you first and this beam came to you a little later, but this latter part, no. So this is interfering with this beam. So, okay, so if you just shine the beam just for let's say a dot, then this will come to you first and this part will come to you later. Okay. But you could never do that. So what we are looking at is we are shining a continuous beam. Yeah? Because the sunlight is coming continuously at you. All right, so this beam came to you. Okay, so let's say this light is red light, and this beam for red light came with the crest like that, and this part of the red light came to you with a trough like that. Okay, so you see, this will happen depending on the thickness of the oil, depending on this angle and stuff like that. So if you're looking at the reflection at this particular angle, you won't see red color. Okay. All right, so this oil slick is not colored. Depending on what you see depends on the thickness of this layer. Okay, so this particular wavelength is destructively interfered. Okay, if this blue color comes like that and this also comes like that, you will see blue. Okay. Now, have you guys seen those cars that go by, and as they drive by, you see different shades? Yes. So what that is on the car, they now are capable of painting an even thickness colored plastic. So at this angle, you'll see one color. At this angle, you'll see another color. All right, so you guys understand that now. So that's constructive and destructive interference of different colors. Okay. Now what we want to understand is the following. So it turns out that when light reflects, okay, when it goes from air to oil, so when it hits like that, it reflects. When a crest hits, when it reflects, a trough is reflected back. Okay, it starts off with a trough. And if it's reflecting from oil to air, if a crest hits, it's reflected back as a crest. Okay, so that's what we want to understand. Okay, and that's important for this kind of phenomenon. Okay? So, for instance, if you wanted to own a business putting that thin layer of plastic on the car, you would have to know all this stuff. Okay, so all right, so. All right, so this is related to all of that. So if you send out a string, you send a pulse on a string, and it reflects on a fixed surface. This is like light coming from air and hitting glass. So upon reflection, see, the positive pulse becomes negative. Okay. If it hits on a free end, a positive pulse is positive upon reflection. So this is like light starting in oil and hitting an air interface. The reflected part in the oil, the pulse remains positive. Okay, so it's related to that kind of stuff. Okay, so let me show you a simulation. Okay, so here's light reflecting off fixed end, meaning when light hits a denser medium, it changes sign, and when it hits a lighter medium, it maintains its polarity. Okay, so light going from oil to air would, when the light beam reflected back in oil, would reflect like that. Light going from air to glass, when it reflects, it would reflect like so. Yeah. All right, so that's what that is about. Okay, what do you think that means?
The wave appears not to be moving.
Right. Okay, so And in fact, it is not moving. So this wave is moving to the right. How do you get it standing is the question, okay? To stand still. Okay, so here is how you do it. What is this guy?
Sine wave moving to the right,
What is this guy?
sine wave moving to the left.
Yeah, and let's look at the parameters. That is the same, that is the same, that's the same. So you have two identical waves moving in opposite directions. How do you do that? You put a speaker here, send waves in opposite direction. And now we're going to look at what is going to happen. Okay? All right, add the two waves. You can use trigonometry to do that. Okay? And here's the result. Okay. See, adding these two waves, here's what happened. Okay. The spatial part and the temporal part got separated. Here is the spatial part, so you can think of this as the amplitude, and there is the temporal part. Okay, for a wave to be traveling, they both have to come in a combination like that. And now this is no longer a traveling wave. Okay. So let me show this to you. Okay, so here this thing is combining a wave that is not traveling with that. Okay, so, and that's the result you get. But, okay, so now what we're going to do is we're going to combine a wave traveling to the right with an identical wave traveling to the left. Okay, and here is the result. Okay, so here is the standing wave. And this is not traveling. Okay. Well, why do we talk about this? What's this got to do with real life? So when you pluck a guitar string, you send a wave down the string. That gets reflected at the fret. And so you have two identical waves traveling in opposite direction. And so on a string, you set up standing waves. That's what happens in all musical instruments. When you play the flute, a wave goes down the flute, it gets reflected on that open end, it gets reflected. So in all musical instruments, you're setting up standing wave. Okay. All right. So, okay, so if it was a string, okay, so you're setting up standing waves on a stringed instrument. Okay, so this string of a given length can only vibrate in certain modes. Okay, so the natural modes are, so the ends are fixed, these are nodes, so these nodes are not vibrating, and antinodes are points which are vibrating with the greatest amplitude. Okay, so this string can vibrate in this mode, this mode, this mode, and so on. And these are harmonic series. These form a harmonic series. So if this guy vibrates with a frequency of 50 hertz, this guy is vibrating with a frequency of 100 hertz. This guy is vibrating with a frequency of 150 hertz, and so on. Okay. So the string vibrates in these modes, and this guy, that's this acoustic, that chamber is an amplifier. Okay, so if you just pull the string, you won't be able to hear it. So this guy needs to amplify that sound. Yeah, that's what that guy is doing. Okay, so the allowed frequencies of vibration for a string are, so there's the velocity of the wave on the string, okay, are n times v, the velocity divided by twice the length of the string, okay, and n can take all integer values, okay. So you see for n equal to 1, bless you, the lowest frequency is given by that, and the higher frequencies are integer multiples of that. Okay, so those are the higher modes, Fn is n times the lowest frequency. Okay, and this is called the fundamental frequency. All right, so it seems like the guitar can only vibrate in certain frequencies. So how come you can play all kinds of music on the guitar?
You can tune it.
Hmm?
I was gonna say different, like, size of wire.
Yeah, so you have 6 string, okay, so you can choose which string to pluck. And in addition, you can change the length of the string by pressing down on the fret to produce all different kinds of frequencies. Yeah. And of course, you're tuning it, you're changing, setting the tension only before you start playing. Okay, so that's what you're doing there. Right, so all musical instruments have some parameter you can change. That's how you're producing different frequencies. Yeah. On a flute, what are you doing? You're opening and closing holes. So if you close these 2 holes, okay, the effective length of the flute is that. If you close all the holes, if these 2 holes are open, then this is the length of the flute you're using and stuff like that. Okay? All right, so this guy, the allowed frequencies form a harmonic series, but a drum, okay, so if this guy vibrates at frequency 1, you see this guy is vibrating at frequency 1.6, 1.59. So they don't form a harmonic series. Okay. Let me show you. So a drum vibrates differently. So there is the lowest frequency at which the drum is vibrating. Okay. And there's the next higher frequency. Yeah. I love this. So there are the modes of vibration of a drum. Yeah. So when you're learning to play the drum, you're learning where to hit on the drum head. Yeah. And so on. All right, here is a very famous problem. Hearing the shape of the drum. What do you think that means?
You can tell the shape of the drum just by hearing the audio.
Yeah, so the question was, so you saw, depending on the shape of the drum, what frequencies it can produce. Okay, so the question is, can you tell by just listening to the music what is the shape of the drum? So this was a famous problem, and it turns out that, see, these 2 drums would produce the same frequencies. You couldn't tell the difference. All right, so what it is the perimeter of this drum and the perimeter of this drum, the perimeter and the area are the same. And they would produce the same eigenfrequencies, meaning the same different fundamental frequencies. So they'll produce the same frequencies. So you couldn't tell the difference between those 2 drums. All right. All right, guys. So the lecture is over.